the row space. So the set of all linear combinations of the row vectors is called the row space of A and is denoted by row A. Okay, it's like the column space, and we write call A. So when we have two vector spaces, let's say here is Rm, here is N, and when we have a linear combination from Rn to Rm, then we can denote that linear combination by a matrix A, where A will be, in this case, A will be of size, it's backward, m by n. Okay, so, and this, the rows of A are vectors in Rn. The rows of A are vectors in Rn. The columns of A, we saw long time ago, the columns of A are vectors in Rm, by the way. So when we take all the rows of A, we got bunch of rows for A, and take a set of all linear combinations of those, that is called row space. And row space lives here, row A, and it is a subspace, by the way. And we know that column space lives in Rm, but row space lives here. Let's do one example. So we got a matrix A given, which is 4 by 5, 4 rows, 5 columns, m by n, and this is row 1, R1, it's a vector, and we can write in terms of a column vector, but that's uncommon because it's a row. So we can denote in this way, R1, and second row, third row, fourth row. And note that this one is in R5. Okay, this is m by n, so n is 5, in fact R5, because we got 5 components. That's why this vector is in R5. And this is R2, R3, R4. So we got 4 vectors. If we write all linear combinations of these 4 vectors, that's what we call span. Span of these 4 vectors, that means all possible linear combinations. That span is a subspace of R5, and that we know that we call row A. So in this example, if we are asked to find row A, that will be just the span of these row vectors. Okay, that's it. Now I'll have an example, several examples how to find them. Okay, theorem. If two matrices A and B are row equivalent, so we have A and somehow we did the row reduction and we got B, which is row echelon form or just echelon form of reduced echelon form or just echelon form of A. Anyways, if A and B are row equivalent, then their row spaces are the same. Okay, if B is in echelon form, suppose B is in echelon form, the non-zero rows of B form a basis for the row space of A as well as for that B. So if this is not in echelon form, then we cannot say anything. But somehow we row reduce and we have now row echelon form B. Then the non-zero rows of B form a basis for the row space of B as well as for A, in fact. So I'll have an example. And finally we have now same thing from last time, the rank theorem. Okay, so what happens is rank of A plus dimension of null A is same as n. Okay, the dimensions, the new thing, what is new here, the rank A is now defined in this way as well. The dimensions of the column space and the row space of an m by n matrix are equal. We define rank A as the dimension of column space, but the dimension of column space is same as the dimension of row space, and we call that common dimension as rank of A, and we write rank A. So that is also equal to the number of pivot positions in A. Number of pivot positions, that could be row or column pivot positions. Generally we looked at the row pivots. Okay, so in general we can write in this way: number of pivot columns, that's the rank. Number of non-pivot columns, that gives us null space, right? That gives us the basis for null space. So number of non-pivot columns, that gives us nullity or dimension of null space of A, that is equal to the number of columns. Okay, that always equals number of columns. And when we have Rn, A is m by n, then we are talking about n. This is n because these both live in n.